Okay, so you might think we're way over time, but actually the speaker started 10 minutes ago. So the next talk is by Tudor Dimofte, unfortunately not on what he announced. I was so happy to be in the title, but on SLNC, Chern-Simons theory at level K. But it's the same speaker. Only the title is.
Yes, thank you very much. I want to
SLNC, Chern-Simons theory.
I want to discuss some ideas that have been floating around for a while and that only very recently congealed, namely on 2 long flights this previous week. The motivation came from the so-called 3D correspondence, which associates, it's physics, associates to a 3-manifold M, possibly with boundary, usually with boundary, a 3-dimensional so-called n equals 2 supersymmetric conformal field theory. A supersymmetric field theory in 3 dimensions, not topological, Tn of n. And so on this side, there's also a choice of an integer n to be greater than or equal to 2. This theory, even though the theory itself is not topological, it only depends on the topology of n. So in a sense, it's a topological invariant valued in quantum field theories. Given this, various observables, partition functions, etc.
Excuse me, what's n on the left-hand side?
I will tell you in a sec.
Okay.
It is an integer greater than or equal to 0.
Or 5.
Various observables partition functions, etc., that one can compute in the theory on the right correspond to more standard topological invariants on the left. In particular, they're things having to do with SLNC Chern-Simons theory. Classical or quantum, depending on what we get. So, for example, I guess the main thing that this talk will be about is that the partition function on a squashed lens space, LK1, meaning in complex coordinates z and w, the lens space is specified by first defining a squashed 3-sphere, d squared c squared plus b minus 2w squared equals 1 inside C2, and then quotienting out by an identification, ZW goes to e to the 2 pi I over kz, e to the minus 2 pi I over kw. The partition function in this geometry, and I will emphasize that the metric really does matter because this is not a topological theory, computes SLNC partition functions, so quantum SLNC partition functions on M for Chern-Simons theory at level K. In fact, complex Chern-Simons theory, as I'll try to explain in the latter part of the talk, depends on 2 levels. One of them is quantized, like in compact Chern-Simons theory, and one of them is not. So the quantized level is K, and the non-quantized one has to do with this parameter B. This particular picture, I should say, became very clear after work of Clay Cordova and Dan Jafferis from Harvard about a year ago. They actually, in the case of the sparse three spheres, they actually did this computation and found Chern-Simons theory. I should say physically, what's going on in Word is that we're wrapping M5 branes, 6-dimensional objects, on a 3-manifold and finding the effective theory in the remaining 3 dimensions. Or one can do that backwards and compactify this on, say, a sphere or lens space and get an effective theory on M, which happens to be Chern-Simons.
Is B real or positive even?
I'll explain that later. It's going to be on the unit circle for most of this talk, but it can be analytically continuous. I mean, here it's just some.
So it's not a lens space.
Things are nice when B is real or when B is on the unit circle. So if you really want the lens space, then sure, take B to be real in this equation.
And should I think of K plus IB, or should I take the log of B?
I'll say that at the end.
Okay.
It's a little more complicated than that.
Yeah.
No, but I don't understand. So it's squashed. It's no longer 3-dimensional.
Sorry?
It's no longer 3-dimensional. If B is not real.
Right. So in order for this washing to make sense, B should of course be real.
But you said B was a root of unity, so if it's also real.
Not a root of unity.
Sorry, on the unit circle, but if it's
Right,
also real,
so-
then its square is not very interesting.
So if one does not care about things like unitarity, you can analytically continue from the real line to the unit circle.
But if you don't do that, does this mean anything if B is not real?
No, it's total. Yes, it does.
But it's 2-dimensional now, not 3-dimensional. And it's very squashed. This manifold is not 2-dimensional.
For this equation to make sense.
No, the
I
equation
want-
makes sense, but it's 2-dimensional instead of 3-dimensional.
Yes, but then I'm going to compute some things using the no. So for this, I want it real here.
Okay.
Real.
That's
It's
what we were driving at.
3-dimensional thing. I'm going to compute some things using that
And then
real geometry and then
Okay.
analytically
Fine,
continue.
great.
Yes.
Real problem.
So with Jul3Thu and Jul3Thu, for n equals 2, we gave a prescription for building up T of m, T2 of m. Starting from a topological ideal triangulation of M. So from triangulation. And being very precise, we're building actually some subsector of this, which is detected by the triangulation. Then with Gabella and Goncharov, which are happily another 2 Gs, we extended to arbitrary n, which simply involves having slightly more refined SLN triangulations, which also appeared in work of Stavros and Chern-Simons. Okay, so roughly the idea of the prescription is to take, say, let me focus on n equals 2, is to take each tetrahedron, associate to it a 3-dimensional chiral multiplet. Which means a boson and its fermionic supercorner. Then glue the tetrahedra together by adding gauge fields and superpotentials. interaction terms. You let the particles talk to each other, and these interaction terms are related to internal edges in the triangulation. This theory T of M should know everything and more about SLNC Chern-Simons theory at all possible levels. So once we have the theory, we can, in principle, compute anything we want. Concretely, given M and N and a sufficiently good triangulation, we get the following things. The classical A polynomial, or in general a variety for higher rank, this is K2 Lagrangian. If you don't know what K2 means, ignore it. It's a Lagrangian that, say, for a knot complement, takes the form A of xy equals 0 in C star cross C star. It's the set of flat. So again, here for a polynomial, I've really restricted to SL2, but there's a generalization for SLN. It's for SL2, it's the set of flat SL2 connections on the torus boundary of a knot complement that extends into the interior of the manifold. So let me actually, for the sake of this little list, let me specialize two knot complements in the 3-sphere and n equals 2, so that I didn't say anything wrong. This, in terms of the theory T of M, is the space of vacua of the theory on an R2 cross S1 on a circle. Then there's this A hat, which has popped up several times at this conference. A hat is, well, it's a recursion relation for the Cohen-Jones. For me, it's going to be an ideal, a left ideal, in a non-commutative algebra, where yx is qxy. This comes up as an identity for line operators. Literally, x hat and y hat are some operators in this theory. And they're line operators in some spinning R2 cross S1 geometry. Where now R2 is fibered over S1 in such a way that it spins by some amount as I go around the circle. And that amount of spinning, that angular momentum, is the non-commutativity parameter. Now, to get to things like Chern-Simons wave functions, we can start computing partition functions on compact geometries on this side. So let me consider S2 times S1 first. So NX times QS1, which means there's angular momentum. So as I go around the S1, the S2 spins by a certain amount. Well, that gives me level K equals 0 Chern-Simons. And on this side, the partition function is called a 3D index. So this is something we studied again with Jul3Thu and Gukov in the context of this 3D correspondence. The invariant takes the following form. I'll call it Z0. So Q of mu and Q. It's a formal, can be thought of as a formal formal Laurent series, whose coefficients, formal Laurent series in Q, whose coefficients are actual Laurent series in mu and mu inverse. For all n. So here, mu is some formal variable. If you want statements about unitarity or actual partition functions, it's on the unit circle. And m is an integer. So one gets a series, an infinite set of Laurent series.
There,
What do you mean mu is 1?
you should get two pairs of integers, and what you wrote is only one pair of integers.
If you Fourier transform it in mu, you get the second
Not,
integer.
it's just a Laurent polynomial.
But what do you mean mu absolute no, mu is 1?
What?
It's
What?
a Laurent polynomial.
Then there's no mu. If it's a polynomial, you don't fix the variable.
Yeah.
Polynomials are functions.
Yeah, he said if you want unitarity.
Yes, sorry.
It
So
doesn't make sense. If you have a polynomial, you can't say something about its variable. You can't define a polynomial and also fix its variable.
well, no, I'm
Yeah, you've
saying
said
that
it's a
it's valued on
polynomial.
the unit circle.
No, you've said it's in z of u inverse.
Yeah, you mean a function with unit circle
Good. So if it's a,
valued in this.
If I change mu, if I change mu,
Just go
is
on.
it the same z of mu inverse or different one? Is it a new polynomial? No,
the
it's
same-
completely different. I mean, is it an element of z of mu inverse for each mu,
No.
or is it
a
a polynomial?
polynomial is determined by its values on the unit circle.
But it's not a polynomial.
Yeah, but if a polynomial, no, but you either give the values or you give the polynomial. You can't do both.
It's not a polynomial.
Fine, I can do one or the other, but I'm talking about the same object. So
But the polynomial doesn't depend on mu. You aren't saying it's an element of z of mu inverse separately for each mu. It's a fixed Laurent polynomial.
it's a fixed
And
Laurent.
as you vary mu, it's the same. It's got the same coefficients.
Yes.
So then
yes.
you can remove mu equals 1. It's just a Laurent polynomial.
Fine.
We can evaluate
Uh,
it later.
It is useful to think about that this polynomial is an actual function on the unit circle. Side, it's useful to think of this as an actual function that does converge to 1. This series does define an actual function when q is less than 1, and mu is valued on the unit circle. And that this actual function is the partition function of the theory on the right-hand side. If I don't care about the actual function, I can analytically continue mu to whatever and get that.
And Q is related to B, how?
B is not in this picture. It'll appear for higher k, so I'll introduce B in a second.
And you said that
Q. Right. So I'll say it now. It'll come back at the end, but just to make it concrete. So the levels of Chern-Simons are k and sigma. They appear in the combination k plus minus I sigma. Sigma is as long as k is not 1, k is not 0, sigma is 1 over I k 1 minus b squared over 1 plus b squared. If k is 0, then I just have sigma. There's no b, and I just have sigma. Q in this case, if k is 0, then q is e to the 2 pi over sigma. So k equals 0 is a slightly degenerate case. The rest of them kind of fall in line. So k greater than or equal to 1. That's the length space partition function I was talking about on a squashed length space. Then, well, for k equals 1, one recovers something that has been called the state integral. First introduced formally by by Hikami and studied by myself with Don and Gukov and Lennels, and then actually properly defined as a convergent invariant by Anderson and Kashaev, and then studied in many other contexts. For k greater than 1, you get some new invariants, which is what I actually wanted to discuss. I will call them, I probably shouldn't write here. I guess it's a little too low. So I will call them Z, E, K of U and E. Here mu is, again, if I want things nice and unitary, mu is real. N is an integer mod k. And this, for fixed B, this is roughly an element of L2 of R tensored with a finite dimensional vector space. I say roughly because this isn't actually, this is what one might want naively from geometric quantization, but there's a better substitution for that involving analytic functions with certain decay and a certain structure of poles, which I don't think I have time to discuss. And I'm happy to talk about that afterwards. Okay. These invariants, Z, B, K, all share some wonderful properties.
Just a question. This is for manifold with boundary, right?
Yeah.
This is for the knot complement.
This is, it's being built from an ideal triangulation, which no matter what you do, there will be some boundary, at least coming from the vertices of the triangulation. You can certainly leave some faces open and do lots of other stuff, which is quite interesting and fun, and has been the topic of some papers. But yes, you will need boundary. There may be some clever ways of filling in the knots in a knot complement by taking certain residues.
Can you not do a span calculation where you just have some balls, some spheres? So for a closed manifold.
Let me tell the story before generalizing it.
Possibly. They don't have good angle structures, but possibly. Have some of the Boltzmann properties. Right, so the plan for however long they have is to state some of these properties, give some examples of these higher level invariants, and then say a bit about quantizing Chern-Simons theory on tetrahedra and knot complements, and explain why the invariants actually take this form and why they live in this particular kind of space. I think I want four properties. Property 1. The invariants associated to single tetrahedra are all some form of quantum bilogarithms. And I've defined, defined over here what they should be. For a tetrahedron, we get something that looks like that. Well, on the left-hand side, I have mu and m, and on the right-hand side, I have x. And I have to tell you what x is. I also have to tell you what x tilde and q and q tilde are. So that formula is valid, again, for k greater than or equal to 1. There's some slight modification for k at k equals 0. So here, x is 2 e to the 2 pi b over k mu plus 2 pi I over k m. So it's a root, a kth root of unity times something involving mu. X tilde is e to the 2 pi b inverse over k mu plus, sorry, this was minus, this is plus 2 pi I over k. And q is e to the 2 pi I over k, 1 plus b squared. Q tilde is e to the 2 pi I over k, 1 plus b to the minus 2. Okay, now what do I have over here? So I've used this q factorial notation. It's extremely convenient to define the q factorial both when q is less than 1 and when q is greater than 1.
Then you should maybe do it correctly. It's q to the minus r in the second formula.
It is. Thank you. Yep. So this makes sense both inside and outside the unit circle in terms of q. In terms of b squared, this I can actually I can match across most of the unit circle. In terms of b, I can match across. I can get a function that's defined in a cut plane. It's very similar to the known structure of the Fadeev quantum bilogarithm, which is what this is when k is equal to 1. Okay. So the local independence of triangulation follows from a 2-3 identity, or a pentagon move. So the 2-3 move is stating the fact that if I take a bipyramid and cut it into tetrahedra 2 different ways, so either into 2 tetrahedra glued along the face, or 3 tetrahedra glued along 3 faces and an internal edge, like that, I get the same invariant. And so 2 quantum dialogues, 3 quantum dialogues. Following the prescription carefully, there's an integral on one side, and there's some identification of variables on the other. So I wrote the formula for k equals 0, but I don't have time or want to explain it. Let me consider the formula for, that's it, for k greater than or equal to 1. So here's roughly the integral. Well, it's an integral and a sum at general k. It's an integral parallel to the real axis on a contour that is well defined, though I'm not going to tell you how. And then a finite dimensional sum. So integral over mu, sum over m, integrate out all of the variables that appear. And right, 2 is equal to 3. So there's some quadratic prefactor mess, but here's the 2, here's the 3. And this depends on 2 pairs of variables, which I've called sigma s and tau t. These are the two free sets of parameters in the identity. Where again, right, so sigma and tau are real, and s and t are integers modulo k. So q q that appears here is b plus b inverse, and there's some prefactor c, which I will mention to anyone who's interested after the talk. Now, convergence of these integrals and the choice of contours and the ability to do 2-3 moves requires, it seems, the existence of a strict angle structure. on the three manifolds. So in the case of k equals 1 for the state integral, Renat had some way to bypass this. And it'd be interesting to see if it generalizes. But at the moment, with these naive definitions, one requires this angle structure. An angle structure is the following thing. For each tetrahedron, we associate angles to the edges, alpha prime, alpha double prime, equal on opposite edges, subject to the condition that the sum is pi around every vertex. Having a positive strict angle structure also means that each of these is between 0 and pi. So that's for individual tetrahedra, and then if we glue up the tetrahedra, the sum of angles around internal edges should be 2 pi. Triangulations of, well, from what Jul3Thu told me a few hours ago, it's recently been proven that triangulations of hyperbolic manifolds always exist with this property, where the inequalities are strict. In practice, one can always find such a triangulation of hyperbolic manifolds. SnapHigh gives one. They seem to exist for torus knots, other knots as well, but they don't exist for something like the unknot. So there are cases when this simply doesn't work.
They also never exist for the connected sum of two knots.
Thanks. Yes. So there are places
said they
where
always exist. I thought you said they always exist by some reasonable result.
for hyperbolic.
Oh, for hyperbolic. But in this long description with three angles, that's just a hyperbolic tetrahedron. This long description with all these
They're reals. This is much weaker than a hyperbolic structure.
A hyperbolic tetrahedron is an ideal hyperbolic tetrahedron is uniquely given by the three angles that are
They're not.
bijection.
That is true, but these need not be hyperbolic tetrahedra.
Right. If you have three numbers that add up to pi and they're positive, that gives you a unique hyperbolic structure.
It does, but my gluing condition doesn't match the torsion. I'm not saying that the torsion going around the edges is 0. I'm just saying that the angle is 2 pi. It's strictly weaker
Right. No, but
than
it's
a
all
hyperbolic
the top part.
triangulation.
All the
Yes,
top part is just
yes,
an ideal.
yes, it is. This is used. Given a triangulation, this defines some big polytope of positive angles, and that polytope is used essentially the way that Renat and Jorn did in a previous paper to find convergent contours for integrals such as this. So
It is not known, even when strict angle structures exist, that you can choose an island of them which is connected by strict 2-3 modes.
yeah, I totally agree. So I can't claim rigorously that what I'm defining is an invariant. It's something that's computed from a triangulation with this property, and I can do 2-3 moves as long as I stay within strict angle structures. I don't know how to bypass that at the moment, but I also there are interesting things to be said despite that. So there are 2 commuting copies of the operated algebra, copy 3. There's this Q commuting algebra, x generated by x hat y hat, and the commuting parameter Q. There are 2 copies of this, in x and x tilde, and y tilde, and q tilde, that act on that act on partition functions. The space of all possible partition functions corresponding to 3 manifolds with a fixed boundary is some version of quantum Teichmuller space. So for k equals 1, this is actually isomorphic to quantum Teichmuller space. For other k, it's some slightly twisted quantization of Teichmuller space corresponding to that boundary. So these operators are acting on that space. Now, if I fix a 3 manifold, that space can also be understood as the Chern-Simons Hilbert space of a 3 manifold with boundary. Chern-Simons at level k.
Do you mean the complexified Teichmuller space or real?
I mean complexified Teichmuller space, but quantization at level 1 of the complexified space is isomorphic to quantization of the real one.
Because the angles are not kept classic, right?
Yes. Well, no, the angles disappear. The angles are quantized. They become integers modulo 1.
In your theory.
And integers in my theory. Integers modulo 1 are not interesting parameters. And all you end up with are some real variables.
So is there a way you can twist it so that it really becomes a quantization of the SO2C character?
Yes, that's what I'm doing.
Yeah.
That's so that's the whole point. This is non-perturbative SL2C Chern-Simons at general level. So as the level goes to infinity, as k goes to infinity, those angles become more and more classical. And so at k equals infinity, you actually get classical angles. But otherwise, they're quantized to be integers modulo k.
More classical or more quantum? More classical or more quantum?
No. More classical. K equals infinity is a classical limit. I mean, there.
But didn't you say k equals to 1 fits with our theory?
It does.
We don't quantize the angles, right?
You don't. Sorry. It's equivalent to your theory. It's equivalent to what you compute. You leave the angles in and you use them to find convergent contours. There's a way to do that without leaving the angles in. The angles actually disappear, but there's an auxiliary prescription for finding the contours. And they're not playing the role of quantum variables in your theory.
This thing classical, so this is...
Yes. But if you want to quantize complex Chern-Simons, you had better quantize everything in sight. There's no such thing as quantizing half the variables. Okay, so fix M. Fix the 3 manifold. Then there are 2 copies of the A polynomial, or the A hat polynomial that annihilate its partition function. There's one in the regular variables and there's one in the tilde variables. And right, so a canonical example of this is the tetrahedron partition function. So if M is a tetrahedron, the partition function is given over on the right. The quote-unquote A polynomial equations corresponding to a tetrahedron look like y plus x inverse minus 1 equals 0. So it annihilates the partition function. And there are 2 copies.
There's no Q? There's no Q in that.
So Q and Q tilde are...
There's no Q in that formula. That seems strange. Oh, I see Q. Oh, I didn't even see all this. Oh my gosh.
So let me tell you how the operators act. So x and x tilde act by multiplication. by x and x tilde, where x and x tilde are given by that. Y and y tilde act by a q shift. So y of a function of x is f of qx, and y tilde of a function of x tilde is f of q tilde x tilde. But to actually write that concretely in terms of mu and m, which is where this comes from, y hat sends mu and m to mu plus ib and m minus 1, whereas y tilde hat sends mu and m to mu plus ib inverse and m plus 1. And those actions obviously commute. And if you translate them into the x variables, you see that they produce the q and q tilde shifts that I commute. It's also trivial to check that they annihilate the tetrahedron partition function written in this kind of factorized form when x and x tilde are separated out. It's just a standard recursion relation for the quantum factorial. Property 4 is holomorphic factorization. So this is conjectural. I suppose I sometimes don't quite. This is conjectural even at the physical level. There are very good reasons it has to be true physically, but there's no physical proof for anything of it so far. I think. The idea is that, so again, I'm going to fix m. So for any given m, the partition function can be factorized into, well, it's a sum of products of so-called holomorphic blocks. So it's a sum over irreducible flat SL and C connections on M. The hyperbolic one and its conjugates, for example. Well, SL and C. I mean, it certainly looks like it holds for general, and the constructions are the same.
Why are there so many B's on the left? Are they the same B or different B's?
Oh, what did I do? I have too many? I have too many.
Well, you have them in your definition too, so I guess it's okay.
They're the same B.
The same B, great.
I just like emphasizing that B exists. So there's B of xq and B of x tilde, q tilde, where B and B tilde seem to be related by, say, having the same convergent hypergeometric series, much like the numerator and denominator in this formula for the tetrahedron function.
But this is not for non-real B, right?
Yeah. So for this to make sense, I need or greater than 1. Absolutely.
And what does the sum mean? I mean, this may not be a finite set.
It's a finite sum. It's connections.
Components?
So it's solutions to the A polynomial.
You mean parabolic to begin with?
No,
Yes.
Well, I want irreducible, which.
But the free manifold has a boundary, so this may not.
I'm fixing boundary conditions.
Oh.
Sorry.
And
X
that's
is
called parabolic, Tudor.
No, it's not. X is playing the role of an eigenvalue of a meridian holonomy
Okay, all right.
on the boundary. So I fixed boundary condition. So if x is not 1, it's certainly not parabolic, but it is iridescent.
Does x tilde as an implication as well?
I mean, it's mu and m are fixing the holonomy.
I mean, it's in the two
X and x tilde are not independent as.
And what is the property of the B alphas to make that a non-trivial statement?
I think it's a non-trivial statement, even if I don't tell you any properties. X and x tilde have been separated out. The defining property is that the B alpha are a set of solutions to the A hat equation.
They're Q
To an A hat recursion.
geometric.
In all examples, this could use a lot of mathematical work. I think it's kind of a wonderful property that is example based at the moment.
Sorry, I didn't understand what x tilde was. Transformed of mu and m.
Yes. So x and x tilde are both functions of mu and m.
Yeah, so x determines the holonomy, and then I just compute x.
Oh yeah. X tilde is related to x.
Yeah. Okay.
That's Q tilde and Q are related to each other.
Yes, they are.
So therefore saying that
But this is a function. This is not a function of. This is an.
Unless you say what kind of a function,
It is-
that's what I meant,
it is-
like
it is-
hypergeometric.
It does not have cuts. It is actually a function of x. There's no. It is a meromorphic function of x and q.
Not of Q. I mean, you can't cross the line absolute value Q equals 1.
With natural boundary. Yes, inside. So q inside the unit.
Oh, sorry, no, that's right. Yeah, so Q and Q tilde do not determine each other, of course.
Yes.
Yeah. Okay.
Right. In particular, in x, there's no. So it's for fixed q less than 1. This is a meromorphic function of x. There are awesome Stokes phenomena that occur as x varies. The basis of blocks jumps, and I think a lot more should be said about that. So I have no idea where I am or how much time I have, or when I started.
You started 15 minutes ago, so
All right, so I have
you
pretty
have
much
a little more time.
Okay.
No, everybody else has gone over, so feel free. Of course,
there's-
you started before you started. That's true too.
So just
There are questions.
roughly, yes.
So dA depends on K, but does it really depend on K?
B doesn't depend on. Wait. B doesn't depend on K. B and K are independent parameters. If I introduce the Chern-Simons level, it kind of depends on B, but
K and B.
they're dependent parameters. The point is, this formula holds for all K, including K equals 0, properly interpreted. So there is a canonical set of holomorphic blocks such that the partition function at any K is factorized into the same set of blocks where the arguments are simply interpreted differently depending on what K is.
But I mean, the B alphas will depend on all the variables.
The B
So you don't
alphas,
have the same
they do
variables on
not-
the left
they're-
and the right, which makes it very confusing. You have a formula where none of the variables appearing on the left reappear, except sort of implicitly.
Right. So I have this set of
Yes, that is.
meromorphic functions of x inside the unit disk, for q inside the unit disk. On this side, I don't really care that there exists a k or a mu or an m or anything.
Well, so those functions just exist, and then you
Those
make these
functions just exist,
substitutions,
and then I
that's
put
the
in
formula.
I put in different substitutions, and I end up computing these invariants for all k.
And the
including
substitutions are the ones here on your left.
exactly.
Okay, makes sense.
So in other words, the theory for k equals 1 determines the theory for any k.
Yes. If yes.
If
Yeah,
this property
yes.
holds.
It determines the 3D index and it determines all higher k.
Okay.
If this highly conjectural statement is believed.
Yes.
There's no matrix in front of it. It's
Yeah, no
really
coefficients.
the alpha. There's no matrix.
There isn't. It's. I think it's a statement that I can pick. I can
You can
diagonalize the matrix.
It's diagonalizable.
It's. I don't have a fundamental motivation for that. It seems to be.
But at least it's a finite sum of this form.
Yes. If you want, you can put it in a matrix. In all examples I know, it's diagonalized. There's no. Yeah. Well, damn it. I can absorb it into whatever I call the alpha template.
It would be weird if it was off diagonal because.
It totally would.
Yeah.
Why is this happening physically? It's because I'm computing 3D. I'm looking at this theory Tn of m and computing its partition functions on a length space, and I'm writing the length space as two hemispheres times S1 glued together with an appropriate element of SL2Z. I'm cutting the length space into two solid tori and doing Dane surgery, an identification on the boundaries to glue them together. The element that I use here tells me which length space I get, but there should be some partition functions associated to the two sides, and those are the blocks. They're labeled by a choice of vacuum. The space has a boundary. The physical partition function doesn't make sense unless I pick a vacuum at infinity, and that vacuum is the choice of flight connection. In that sense, I elongate this so that there's a unique vacuum in the middle, and so I kind of expect a diagonal factorization.
So all abelian connections are included in this one?
No, they're not. No, they're not. And so the invariants that are being computed are, if you want to say, some subsector of Chern-Simons theory that sees irreducible connections. So when considering a complexified group, there is a huge difference between abelian connections and others. This stabilizer group is very different, and there seems to be a consistent formulation of the theory that only includes the irreducible connections.
So this is only part of the full Chern-Simons?
It is only part of the full Chern-Simons, but I have trouble believing that, again, from computations, that the full partition functions are finite without some extra regularization. In order to include the abelian connections, some extra parameters need to be added. Otherwise, you just get infinity. Right. So let me keep going and finish up. So I keep claiming that this is Chern-Simons. Let me just explain where the variables come from. I'm going to erase this. So fun exercise. Let's try to quantize a model phase space in complex Chern-Simons theory. So take a phase space that's C star across C star. This is, for example, the phase space of a tetrahedron of the boundary as given in cluster coordinates. Or if I divide out by Z2, it's the phase space of SL2 theory on a non-complement, where these are longitude and meridian eigenvalues. It comes with a holomorphic symplectic form, where x and y are the two C star variables. But of course, that's no good for doing an actual quantization. I need a real symplectic form, and that's where the levels come in. So the real form turns out to be k plus I sigma omega plus k minus I sigma omega bar.
This is the real part times the complex constant, right? I mean, constant.
It's the real part of k plus I sigma omega. And here we get the quantization for condition for k, provided that the periods. Well, if we ask that the periods of this real form are quantized, k has to be an integer because there's a non-trivial two-cycle wrapping the unit circles inside the C stars. Now we make two incredibly convenient substitutions. One of them I've written already here. I reparameterize sigma in terms of b. And the other one I've written on the board on the left, I reparameterize x and y. So let me do it here. So x is 2 pi b over k mu minus 2 pi I over k m, and I'll set y to be e to the 2 pi b over k mu minus 2 pi I over k m. Where a priori m and n are not necessarily integers, they are real and periodic, obviously, because x and y are C star value. So m is the same as m plus k, and the same with n. When I do that, the symplectic form diagonalizes quite beautifully. It becomes 2 pi over k d mu wedge d mu minus d m wedge d m. So what happens? I can quantize each pair separately. From mu and mu, I essentially get a copy of, I would like to get a copy of L2 of R. And from M and N, I get the finite dimensional space I mentioned. How does that work? Well, M being periodic, quantizes n, and vice versa. And they're both periodic and they're both quantized, so of course they have to take values in z mod kz. And at the end of the day, I can represent my Hilbert space as functions of mu, of half the variables, say mu and m, where m is valued in z kz. And it's a little exercise to check that the operators you get by quantizing everything, by quantizing mu and n, you get y and y tilde, which acts the way that I've claimed. That's where the finite piece comes from. Again, if k equals 1, this is gone, and you just get something that looks like L2 of R. The other fun fact is that, well, where do q and q tilde come from? Given this substitution, this definition of sigma, q is the inverse of the holomorphic coupling. It's 4 pi I over sigma plus I, over k plus I sigma. It's the exponential of that, which beautifully is the expression on the other side, 2 pi I over k, 1 plus b squared. And same for q tilde. That's how the quantization goes. And I'm out of time.
Now maybe slowly out of time. So let's thank Tudor. Maybe very short questions over 30 minutes overtime, and in 5 minutes or something we get our calligraphy. So maybe very few and the rest privately. Actually, we've been asking questions the whole
Can you
time.
just comment briefly on why you don't use all lens spaces, but just K, 1?
I should use all of them.
I have the same question in inverse. Why don't you use SL2Z instead of just 1/k? But I think it's the same.
It's the same.
This transformation is a very special SL2Z.
Yes, you absolutely should. I don't know exactly what Chern-Simons theory it gives you. The reason LK1 is level K is because it's a Hopf vibration of degree K. There's an S1, the rest too. And it's the degree of that Hopf vibration that through some chain of arguments leads to the level of Chern-Simons. The other ones are not like that, but they should lead through something. And I assume that they're just going to shift. So if I look at LKP, I assume that they're just going to shift the roots of unity that appear in Q and so on.
No, the relation between B and B squared also changes. The relation is tau prime is A tau plus B over C tau plus D. And that matrix will become more complicated. Right? You now have the matrix 1, 0, K, 1.
Yeah.
You cannot put 1, 0, K, P because that doesn't have determinate 1. So you have to take, P prime, K prime. It's more complicated.
Yes.
But there is.
Yeah. Okay.
It's just SL2Z.
Yeah.
Yeah.
Okay.
And the SL2Z only works in the obvious way if it's K, 1. But it always works.
Just any idea what you would get if you took a hyperbolic manifold LKP?
No. I'm not even. So the computations in these kind of nice symmetric spaces with circle actions are very special. They're done by supersymmetric localization, and that's. I would love to even know what happened for a Seifert manifold. I really don't know. It's possible to. It may not even be possible to preserve supersymmetry. I have to think about that, and it would be very hard to compute.
So it probably wouldn't be something that like the Chern-Simons for a lead group, right?
I don't know. It probably not.
Since all questions have been answered, let's thank the speaker again.